we can think about this complex number as its real component and its imaginary component. Okay? So let's say this is the complex number 4 plus 3i. So that's the complex number 4 plus 3i. We could figure out the magnitude of this using the Pythagorean theorem. So this guy here is 4. This guy here has a length of 3. We'll call it 3i, but its magnitude, well, let's go like this. This is a kind of a funny looking absolute value sign. It's what we're going to use for the magnitude. The magnitude of the imaginary part is equal to 3. The magnitude of the real part is equal to 4. So consequently, the magnitude of the entire number, a squared plus b squared equals c squared. And you guys might be familiar with 3, 4, 5 right triangles. And you know that the magnitude of this guy is 5. Is this notation okay for you? It's kind of like absolute value. We're just talking about the magnitude of that complex number. So we've got a complex number which has a magnitude of 5. And you can see triangles are going to rear their ugly heads real quick. Okay. Does this make sense, everybody? Okay. So, in general, the magnitude of x, well, I'm going to use this letter instead. The magnitude of z is equal to the square root of the square of its two components, the sum of the two components. Does that make sense, everybody? The distance along what we would call the x-coordinate, the real coordinate, the distance along the imaginary coordinate squared. A squared plus b squared equals c squared. So that's how we're going to talk about the magnitude of that thing. Make sense?
The magnitude of what?
If I have a general complex number, I'm going to call this number here, I'm going to call it z.
So z just a general complex.
Yeah, just a random schmuck complex number. So that's why I put the real part of z here, the imaginary part of z here. I'm going to take the real part of z and square it. Just to be on the clear side, Paul, let's go like this. Boom and boom. Duh, we gotta figure out the real part of z first and then square it. We don't want to square z and then find the real part. Okay? So, beautiful. So, we've got this idea of this, and now I'm going to even go one little step further into abstract land. I'm going to take away the fact that this is a specific real number and just talk about it as a general real number, z. I'm going to call this, the magnitude of z is this distance from here to here. Okay? And I'm going to call this, for want of better words, because I'm not good at knowing the right words, I'll call that the angle that z is at. Okay, does that make sense? That's the angle. Okay? And can anyone figure out what, using SOHCAHTOA, shoot, I don't know a better way to say it. I'll just use it myself. Using SOHCAHTOA, we know that this times the cosine of my angle is going to be this distance. SOHCAHTOA, let me go like this. For this angle, this is the opposite, this is the adjacent, and this is the hypotenuse. And the opposite over the hypotenuse, works out to be the sine of the angle. So I can call this the magnitude of z multiplied by the sine of theta. And I'll call this the magnitude of z multiplied multiplied by the cosine of theta. Well, what the heck? Why am I doing all this? What this does is it gives us another way to write out complex numbers. Instead of thinking about complex numbers in terms of things like, where are we at? Instead of thinking about complex numbers as things like -2 plus 3i, I can start thinking about them like this. It's the cosine, I'm sorry, it's the magnitude, I don't know why, but I'm going to use the letter R, R for radius, the radius of, you know. It's the magnitude times the cosine of theta plus I times the magnitude times the sine of theta. So this lets us, what this allows us to do is hopefully make sense of some of this idea where if I take two of these things and multiply them together, I can add their angles. It allows us to talk about these things in terms of the angles. The whole reason that we wanted to do this is to do that, is to be able to do that. Yes, Carl?
Do you want a magnitude B instead of an R there?
I absolutely
Right there, so it's
do.
consistent.
Thank you. I'll do it in pink, just so everyone can see the mistake I made.
I'll zoom in.
Okay. Is everybody cool with that?
When you plotted these complex numbers here, how do you get the angles from that? Is that just from the slope or
How did I get those angles?
from the protractor?
I
Use the protractor.
I use the protractor to find these angles, and of course, when we're dealing with
But you can use that
Calculus.
for the slope of the line, you can use the protractor to calculate that.
yeah. Now, just to be on the safe side, Paul, when you're dealing with calculus later, we're going to have to be thinking about angles measured in radians, not in
Yeah.
degrees, because the issues that the derivative of angles measured in degrees have. But what I did here is I just showed you what happens, and now I'm going to try to explain maybe why it happens. So let me do some algebra, and I think the best place to do algebra is right here. So let's get two complex numbers. And I'm just going to go back to R. I'm going to call one of them R1 times the cosine of angle A plus I times R1 times the sine of angle A. And I'm going to take that complex number and multiply it by this complex number. Let's do it in a different color than red. It's a different number, so it's going to have a different magnitude. We'll call that magnitude R2. And it'll have a different angle. We'll call that angle B. It still is going to have a real component and a complex component. But we end up with something that looks like this. So I'm going to take the green number and use the distributive property /FOIL, to think what would happen if I multiplied this times this. So let's do that thing. We end up with